Mercury is an extremely toxic element to humans and the environment, often found in natural water sources with a low elimination rate from organisms. Mercury found in the human body usually occurs through the consumption of fish and seafood products, where bioaccumulation occurs from the environment. Mercury has extremely harmful effects to the central nervous system, even in the low concentrations, and therefore a highly sensitive quantitative technique must be employed for the detection of mercury in the water samples.
Atomic absorption spectroscopy, also known as AAS, is widely used for the analysis of metallic and non-metallic elements. Magalante describes AAS in two steps, where analyte molecules undergo atomization into gas phase atoms, followed by atoms absorbing radiation. Through the ability of components in the analyte to absorb radiation, the concentration of these species can be measured at a particular wavelength using Beer's law. Normal AAS uses either flame or electrothermal methods for atomization. However, cold vapor atomic absorption spectroscopy, CVAAS, uses a chemical reaction to reduce the analyte component of interest into a volatile product, and therefore no vaporization step is required. The volatile element is then carried by an inert gas into an absorption cell. Instrumentation for AAS includes a radiation source, an atomizer, a monochromator, a detector, and finally a readout device. A hollow cathode lamp serves as the radiation source, consisting of an anode, a cathode, and an inert carrier gas. In CVAAS, the anode is typically made up of tungsten, while the cathode is made up of the element being analyzed. An experiment using CVAAS for the determination of the mercury 2+ ion and methylmercury in water samples was performed by Tuzin et al. A standard solution of 1,000 mg per litre of the mercury 2+ ion was prepared from mercury chloride, in addition to another standard of 1,000 mg per litre of methylmercury from dissolving methylmercury chloride. Mercury ions were reduced using sodium borohydride, and samples were filtered through millipore cellulose membrane filters. A mercury hollow cathode lamp was installed onto the AAS instrumentation, serving as the radiation source, with argon serving as the carrier gas. The AAS was ran at a wavelength of 253.7 nanometers to generate a spectrum, where concentration of mercury was able to be determined. Table 1 shows results of the concentration of mercury ions and methylmercury found in a tap water and seawater sample. The experiment found CVAAS had a detection limit of 2.5 nanograms per litre for the analysis of mercury ions, while methylmercury had a detection limit of 1.7 nanograms per litre. This overall proves that CVAAS has the ability to detect mercury at extremely low concentrations.
Inductively coupled plasma mass spectrometry, or ICP-MS, is an analytical technique used to determine the elemental composition of a sample. It works by converting a sample such as mercury into a plasma by adding an acid to it, which is then ionized and passed through a mass spectrometer. The results can be put into a calibration curve using other concentration standards to determine the concentration of the unknown amount of mercury. ICP-MS is sensitive. It can detect elements at concentrations as low as parts per trillion, making it an ideal technique for analyzing traces of elements within a solution. Additionally, ICP-MS is fast and efficient for analyzing large numbers of samples in a relatively short amount of time. Despite its many advantages, ICP-MS is a complex and expensive technique that requires specialized equipment and expertise. However, the benefits of ICP-MS make it an invaluable tool in many scientific fields. The process of measuring mercury using ICP-MS involves sample preparation, calibration, instrument setup, and data analysis. By following these steps, scientists can accurately and reliably measure mercury in a wide range of samples. In sample preparation, the sample must be prepared before it can be analyzed using ICP-MS. In the case of a mercury analysis, the sample is typically digested using a mixture of acids to break down any organic matter and release the mercury into the solution. In calibration, once the sample has been prepared, the instrument must be calibrated. Calibration involves analyzing standards of known concentrations to create a calibration curve that relates signal intensity to mercury concentration. During part 3 of instrument setup, the ICP-MS instrument must be set up to measure mercury. This may involve adjusting the instrument parameters such as the plasma flow, sample gas flow rate, and mass spectrometer settings to optimize sensitivity and reduce interference from other elements. The prepared sample is then introduced into the ICP-MS instrument. This is typically done by nebulizing the sample and introducing it into the plasma using an argon gas flow. Once the sample is introduced into the plasma, the mercury ions are ionized and separated by mass in the mass spectrometer. The detector then measures the signal intensity at the mercury mass to determine the concentration of mercury in the sample. In data analysis, the data generated by the ICP-MS instrument must be analyzed to determine the concentration of mercury in the sample. This involves comparing the signal intensity of the sample to the calibration curve to determine the mercury concentration. To ensure the accuracy and reliability of the results, quality control measures must be implemented. This includes analyzing blanks and standards to assess instrument performances and detect any contamination or interferences.
A study by Nixon, Burett, and Moyer used a series of samples and 2 blood samples containing mercury for quality control while investigating levels in whole blood and plasma through ICP, MS, and CV-AAS. Results from Table 1 show the CV-AAS method had an overall lower standard deviation, suggesting a higher precision than the ICP-MS method. This is due to a margin of error ranging from 1.9 to 3.5 micrograms per litre, whereas the ICP-MS ranged from 1.6 to 8.6 micrograms per litre. Both samples showed an equal number of results that were close to the stated concentrations, suggesting they both had the same accuracy. The CV-AAS method for measuring the NIST 2670 elevated sample showed results of 86.6 plus or minus 1.9 micrograms per litre, as opposed to the stated concentration of 105 plus or minus 8 micrograms per litre. This suggests there may have been losses to the sample, which may have occurred through the pre-sample treatment required for CV-AAS. CV-AAS and ICP-MS both prove to have low detection limits. The techniques differ in that CV-AAS requires little interaction from the operator, whereas ICP-MS operators often need to be trained. CV-AAS is also relatively inexpensive, while ICP-MS is quite costly. ICP-MS does offer an advantage in that it is able to detect isotopes and only needs a small amount of sample. However, this sample often needs dilution to combat matrix effects. CV-AAS has a major limitation in that it is a method limited to the detection of mercury and not widely known to be used on other elements. Picking a method for the detection of mercury ultimately is down to the sample and availability of equipment. CV-AAS is often used in laboratories due to it being more cost-efficient and little interaction is needed. However, it also depends on what the sample is being analysed for, such as other elements involved, where it may be beneficial instead to use ICP-MS.